Welcome back, everyone. This would be day 2 of College Algebra 1. The lesson is 1.2, the real numbers. Alright, so for this unit, this is going to apply for the entire trimester. We're not going to be dealing with imaginary numbers in this trimester, only the real numbers. The real numbers consists of two sets of numbers called rational numbers, designated by the letter Q, and irrational numbers designated by a capital letter I. The real numbers themselves have their own unique symbol. It's this modified capital R. It just has a double line over there. The book or the computers, they have a little more unique way of writing it, but that's the way we write it when we're doing it by hand. Alright, let me see. I usually start with the very center here and work my way out, but since this is not an order of operations or like a union intersection where I have to work for the inside out, I can work in any direction I want. Let me see if I got the right pen. I might need a couple of these. Alright, so here's the definition of rational numbers. A rational number is any value or any number that can be written as the ratio of two integers. Well, we need to find out what integers are, and we will, but we use the capital letter Q because R is already taken for real numbers, and they didn't want to use an A, T, or any of the other letters that followed. They used the letter Q, and I believe they used the letter Q because this is the answer to what we call a division problem. If I take the ratio 2 divided by 5, this is a ratio, also known as a fraction. And so if we want to turn this into an adjective, we would say this is rational. I have one integer over another integer. And its answer would be the quotient. So that's how they arrived at rational numbers designated by the capital letter Q. So here we go. Let's try this one. It's going to be, I don't know, 9 over 4. Doesn't have to be what you've learned in the past as a, like, I don't know why. I don't like this designation, improper fractions, but I'm not going to get into that. There's no such thing as improper fractions in my class. All right, everyone's welcome. Let's go with the negative 2 over 5. Let's go with the positive 7 over negative 8. Now, do they always have to be fractions, or at least in their fraction form? Nope. I can take this number right here, the number 12. That's rational. Why? Because I can write it over 1, and now it's truly, visually rational. Doesn't always have to be a whole number or fractions, per se. Doesn't have to look that way. We can turn it into a decimal. In its decimal form, 1.5, the decimal will either terminate, that just means end, or it's going to repeat in a pattern, a predictable pattern. 0.3 bar, which is the same as 1/3. All right, so that is a list of all the rational numbers. How many rational numbers are there? An infinite amount of rational numbers. Too many to count, more than the stars in the sky. Next, we'll talk about a subset of these rational numbers. And the first subset that we're going to talk about are integers. Now, we have a tiny problem again. We've already used capital letter I. We'll never use a lowercase letter. Besides, the lowercase letter is already taken by imaginary numbers, and we said we're not going to deal with those this trimester. So what letters can we use? Well, it's so much of a problem that it depends on what textbook you're looking in. Like our textbook, I believe it uses the letter Z. Other textbooks around the world use the letter J. I don't have any fancy story of why they use those other than the phonetics or how it sounds, the phonics rather. Integers, don't know why they didn't use a G there, or integers. If you want to get a little crazy and misspell this integers, I I don't misspell it, but I do emphasize the way I pronounce it. Integer, integers. So I think of that to remember the designation for integers. J or Z. Now I'm going to write some examples of integers in a weird location, but just trust me on this. I'm going to put them way down here. So these are what the integers are. They're all of the negative and positive numbers that can be written kind of like this guy here, kind of like what we would call counting numbers. Like they include the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to infinity, but they also include the opposites of those, like -1, -2, -3, -4, -5, but they also include the number 0. So I'm going to just write it like this. It's going to be all the way from negative infinity all the way down to -3, -2, -1. I'm going to stop there. Those numbers don't stop, but you're going to see why I stopped there in just a second. Let me see how we can... I'm going to have to box these up like a nice Christmas gift. Okay, so I'm going to come down like this and over like this. Yeah, that works for me. Let's talk about a subset of the integers. The next subset of numbers are a set of numbers called whole numbers. Let's turn that into a happy O. You'll see why I do that. Everything I do, there is a reason for it. And sometimes it's very obvious and clear right away. Other times it takes a little while to figure it out. Whole numbers, designated by a capital letter W. Yeah, I think I left enough room in there. Now, whole numbers do not include these negative numbers. Whole numbers consist of non-negative numbers. And I'm actually ready to put a box around this real quick. Let me see if I can do this. Sure we can. We can always do it. Here's why I did that and emphasize this. This number right here, I know it's a letter, but turn it into a number. What number does that look like? That looks like the number 0. The smallest whole number begins at the number 0. Whole numbers start at 0, and then they go how? They go to our final subset of numbers, and those are the counting numbers. There is another name for counting numbers. They are called the natural numbers. Designated. The set designation for the counting or the natural numbers is a capital letter N. We've already seen this in 1.1. And here are the numbers that consist or that make up the counting natural numbers. They're the numbers you learned as a child. Those are the first numbers that you ever learned to count. They are the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, forever to infinity. Now, I need you to make sure the way that we drew this picture, it kind of looks like there's more rational numbers than integers. There's more integers than whole numbers. There's more whole numbers than counting or natural numbers, and that is not true, because there's an infinite number of every one of these sets. Counting or natural numbers are subsets of the whole numbers. Whole numbers are subsets of the integers. Integers are subsets of the rational numbers. And rational numbers and irrational numbers are subsets of the real numbers. And there's an infinite amount of every one of those types of numbers. All right. Now, if you look by my color code here, I hope that makes sense to y'all. If not, just ask me anytime you have questions, all right? Let's talk about these irrational numbers. The most famous irrational number of all is pi, the number pi. And we learned it as just 3.14, but it's way more than 3.14. It goes on infinitely forever, and it doesn't ever repeat. There's another number like that that occurs in a lot of different things outside in the natural world. So we call this the natural number e. I believe if you're coming from 3B, y'all use this when you were dealing with logarithms. Log base e, or natural log. It's a very important number, and we will discuss it later. We also have some square roots here. Now, it's not just the square root or cubed root or fourth root of any number. It needs to be one that cannot be simplified all the way down and actually get rid of the square root. I'm not going to put a 1 in there because that actually simplifies to 1. The square root of 1 is 1. I'll start with the square root of 2, or radical 2. I'll continue with radical 3. I will skip radical 4 because radical 4 is the same thing as, rad 4 is the same thing as the number 2. So if you see a pattern, basically it's going to be, if I'm dealing with square roots, it's going to be the square roots of any non-perfect squares. If I'm dealing with cube roots, it's going to be dealing with the cube root of non-perfect cubes. What is a perfect square? Pick any counting number. Actually, pick any integer. Any integer out here whatsoever. Okay, I like 3. Square it. 3 squared is 9. If I put radical 9, I know that simplifies to the number 3, and I cannot use that. It's not irrational. It should be thrown over here in, well, I would throw it into the counting numbers. Okay. Other examples of perfect squares are the numbers. All I'm going to do is take these first few numbers and square them. These are perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. You should memorize your perfect squares up to 20. You should know what any number between 0 and 20, or actually negative 20 and positive 20 is if you square it. Here's one more example that I like to use because just always got to consider as many possibilities as we can. All right, I'm talking about the number 0.1234. If I stopped there, if it terminated, it would be a rational number. But I'm not going to stop. I'm going to keep going. 5, 6, 7, 8, dot, dot, dot. Those dots in that order are called ellipses, and they just mean so on and so forth in that pattern. Now, over here we said a repeating pattern. Do you see any numbers repeating? Do you see a repeating pattern? Or do you just see a pattern? It cannot just be a pattern. It has to be a repeating pattern of numbers. Like if it was 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4 with a bar over the 1, 2, 3, 4. Or a bar over anything. Any bar means that it's a repeating pattern, and it would be considered a rational number. Anything else is irrational. All right, some of y'all cannot see the top of my desk, but if you could, you'd see these highlighters. You can pause it at this point and go get you some highlighters. You're going to need highlighters for this next step. I'm going to draw a quick number line here. I'm going to do the same here. Maybe I went too far. I just wanted a tiny one. And a final one. I need to put this on the pre-notes next time. Alright. So here's what's going on with these right here. I went a little too far. I'm going to cut that off there, and then I don't know, I'll figure out the rest from here. So what we got going on here is an inequality. This is pretty much basic algebra or integrated 1A or 1B. Basic graphing of these inequalities. I'm going to use the visuals to help explain what interval notation is. So I'm going to start this guy at 3, and I'm going to run it to 7. It means my answers, my x values can be anywhere from 3 to 7. This is read as 3. Oh, I'm so sorry. Let me bring this up. My goodness. Good thing I looked at that video. Try it one more time. Sorry about that, guys. One more time. Here we go. We are going to say 3 is less than x, which is less than 7, or 3 less than x, less than 7. Notice I did not say less than or equal to, so these are known as my endpoints or my critical points. I think some other books call them boundary points. As you notice, I circle them. The book will not. The book will use a different symbol, and I will get to that symbol in a minute. Well, what we're going to do with this is, here's where that highlighter comes into play. I'm going to shade everything between 3 and 7. And that's what the graph of it would look like. Very clean, very neat, very professional. Now, I want to write that in something called interval notation. What is interval notation? It's going to use these types of parenthetical symbols. We've used braces before for something called set notation. For interval notation, we are either going to use parentheses or brackets. In this situation, where it does not include the endpoints are excluded, I'm going to use parentheses. I'm going to say the open interval from 3 to 7. That's what I say. That's what I write. Notice I use this word here, the open interval. It's opened. That means it's not shaded in. That means the endpoints are excluded. Fancy word for not included. Now, I said the book does it a little bit differently, at least their graphs, if they ask you to graph it. They don't use open or closed circles at the endpoints. They actually use this symbol here. So they would use a parentheses here. Let me just show you how the book would write it. And you can pick whichever way you want to do it. They would say 3 to 7 and shade everything in between. Now, I don't know if I'm going to start using those parentheses. I just haven't. I know that you came to me using opened intervals like that. Hopefully you can see that's supposed to be open where it's not shaded. Yeah, that's good. Either way you write it, I'll accept them both because they are both correct. Now, using the same numbers, but having a less than or equal to sign here and here, what I'm gonna do is close those intervals or shade them in because now they are inclusive or included. And the way you write it in interval notation, the way you write it in the college algebraic way is bracket. This is the closed interval from 3 to 7. It is a closed interval, and all that means is the endpoints are included. Now, there's no rule that says if you start off open, you have to finish open, or if you start off closed, you have to finish closed. You can have intervals that are opened on one end and closed on the other. That's okay. It's perfectly okay. And that's the situation we have here. It's closed at 3, but opened at 7. I'm going to show you how that shading looks. first. Y'all know. Close it up at 3. Shade it in. Shade in between the 3 and 7, but leave it open over there at 7. So how do you write that in interval notation? Well, we're going to say the interval, the mixed interval, that is closed at 3 and opened at 7. Just like that. So in the book, they would have a bracket at 3 and a parentheses at 7 and shade everything in between. Mixed is okay. It's called a mixed interval. And what happens was, anytime it's closed, use a bracket. Think of it this way if you have a hard time remembering it. If there is a straight line under your inequality symbol, use a straight line as your parenthetical symbol. If there is no straight line under that, use a parentheses. All right. Let's take a look at example 1 today. We want to graph these two sets on the number line, and the first one says the set of x's such that x is a whole number less than 4. I need this. What does this bar right here mean? This vertical line, if it's only one of them, right here and down here. It means such that. Can you see that? Yesterday it was off the screen. Yeah, that's legible. Such that right here and right here. I want the set of x's such that x is a whole number less than 4. All right, looking up here, what are my smallest whole numbers? Well, my smallest whole number starts at 0. So I'm going to go ahead and start this at 0 and then count 1, 2, 3, 4, 5. Didn't have to go out that far, but I did. And what I'm going to do is I want all the x's that are whole numbers less than 4. So I'm not going to include 4. I guess the book might have, but it left it open. I think that's just silly. It's useless. I'm going to include 0. I'm only going to circle the ones that I'm about to shade in. I'm going to include 1, 2, and 3. And let me see. I'll grab this highlighter this time. Doesn't matter what colors you use, just use highlighters, please. Those pencils, that gray graphite pencil, is a little boring. I also wanted to bring up something too. I know other teachers have taught you to do this or let you get away with this. Let's say it was like this right here from 3 to 7. I don't care if it's open or closed right now. That's not my point. Some of you have done this. Please don't do that. Please don't do that. That's actually a whole different thing. That's called like a sine or a cosine wave, and that's not what it is. Please don't do this either. Guys, don't be lazy. I know that there are some kind of colors in your house. I don't care if you use Sharpie highlighters. I don't care if you use colored pencils. I don't care if you use your little brother's or sister's crayons. But I do want it to be neat, complete, and colorful. I need it to look like that. Oops. I need it to look exactly like that, or as close to that as possible. Okay? All right. There could have been another way that we actually wrote this set. A lot easier way. They could have just said, FYI, I want the numbers like we learned them before. We could have said the set 0, 1, 2, 3. But then it would have given it away. So they want to kind of make sure you can solve this tiny mystery puzzle. And that was your opportunity to do that. Let's look at 1b. I need the set of x's such that x is a real number greater than or equal to 7. So it's going to start as small as 7. That's going to be the smallest value it'll ever be. It says or equal to, so I'm going to close that up. close that up. And then it says greater than or equal to. Well, here's where I don't want kids to just say greater goes to the right, because it matters the order I wrote that in. You need to pick you a test point. Pick a number over here. 8. Is 8 greater than or equal to 7? It is. So I'm going to shade to the right of it. I'm going to shade in that direction, I should say. And we are done with our first example. Flip the page. For our last example, I picked these types of problems because these types of problems, as you can see, are the most missed problems on any test. These are the problems that kids miss most. So I want to jump right into these, how to handle them. I give you a number line to use, but that's not going to actually be your final answer. It's just a tool that you use to try to get an answer. Here I have two intervals. I have the open interval from 2 to 4 and the closed interval from 3 to 6, and I want a union of those two. So the first thing I'm going to do is, I know this means the word or. I'm just going to write that above it. The second thing that I'll do is, I'm going to take my first interval and throw it down here. I'm going to go from 2 to 4. I am going to float above it. I think that was another way, that was another pet peeve of mine, that kids, when they're asked to graph, they do something like this. I only use that. I think some teachers misunderstood it. Some teachers that aren't as experienced in mathematics, and they teach, oh yeah, that's the graph. No, it's not the graph. First of all, it's not on the number line, it's above the number line, and it's just wrong. But I'm using it right now as a tool to see where these two overlap. This is my prep work. It's kind of like a rough draft, if you will. The next thing I want to do is, they want me to, or I want to take this right here, and I'm going to go from 3 to 6. That's representing that I'm shading those. And I'm going to go here. I'm going to write one more note. Anytime it says union, which means or, you want to include in your final answer anything that is shaded. You're looking for shade. Alright, so what's shaded? Well, here's what I notice is shaded. I notice that it starts at 2 but does not include 2. And then it includes everything between 2 and 3, including 3 and 2 and 4. Now 4 was not originally included over here, but it is included in my pink, or my second interval, so it's going to include this as well. And then it's going to go all the way to the number 6 and stop at 6, but include 6. So one last thing I'll do with the swipe of my purple highlighter. Like I said, start at 2 but not include it. Go from 2 to 6, include 6. And write your single interval like this. It's going to be a mixed interval. It's going to be the interval open at 2, closed at 6. There is your final answer. Alright, using the same numbers, but the other joining symbol, the intersection. And I'll throw this right down there. This looks like the letter what? It looks kind of like one way we write the letter A. I'm going to do the same thing. Y'all already know the drill. I'm going to put this on the number line. I'm going to go from 2 to 4, opened on both ends, and shade between. Then I'm going to go from 3 to 6 and shade in between. And literally and. When it says and or an intersection, when it says and or the intersection, you're looking for where the shades overlap. There's that A again. Where do they overlap? What does that mean, overlap? Well, if this was, well, what is blue and pink or blue and red type of make? Kind of makes a purple. Over here, all I have is all blue. On this side, all I have is all pink. Over here, I have blue and pink kind of going on right here. So what this is saying, it starts at 3. Is 3 included in both of them? If you're not sure, go back over here. Is 3 in between 2 and 4? Yeah. Is 3 between 3 and 6 including 3? Yes. I'm going to go from 3 to 4. Although 4 is included over here in the pink, it's not included in the blue. It's excluded, so I'm going to leave that open. And, oh, I don't know why I don't just go to my highlighter right now. I'm going to go from 3 to 4. It is closed at 3, but open at 4. Okay, we have another mixed interval. I'm going to go from 3 to 4, and it's closed at 3, opened at 4. And that is how you use your number lines. Finally, yeah, I'll still use the same colors I've been using. I'll do that interval. We're going to try to write it. We're going to try to combine it and write it as a single interval instead of the union of two intervals or the intersection of two intervals like we did for part B. Let me see. I'm just going to put a -1 over here. By now, you kind of see what I'm doing there. That just means included. I'm going to go from 1 to 4. Opened at 4. Closed at 1. Then I'm going to go from 0 to infinity. Closed at 0. And it just goes towards infinity. Forever like that. Let's take a look at this. This is a union. Union means or. So I'm looking for any shade, anything that's shaded. Well, here's what's shaded. It starts at -1, including -1. And it goes all the way in this direction to the right forever. It includes -1. It includes all the numbers between -1 and 0. It includes 0. It includes all the numbers from 0 to 4. Does it include 4? Well, do you see how even though it's opened on the first interval, it's closed on the second interval? It goes from 0 to infinity. So as long as it's closed in either or, either this set or this set or this interval rather, then it is included in our solution. So we're going to start at -1 and run it to infinity. That interval will be written this way here. We're going to go from -1, include it, so close it, to infinity. Now, in my class, I choose to use a parentheses at infinity, and let me tell you why. To me, I feel it has to be tangible, or you have to be able to reach infinity and graph it. Since you can never reach infinity, just when you think you're there, you got to go more. And once you think you're there again, you got to go more. You're never going to get there. I had professors in college that taught me this, but this is also an accepted answer. Well, at least in my class it is. And in any smart teacher's class, it should be. We're going to start at -1 and close -1. There are other professors that say, I'm going to go from -1 to infinity. but I'm going to put a bracket on infinity because it includes infinity. And that's their train of thought. And that's okay. I believe they have a valid point. I believe both versions have a valid point. And I'm going to leave it at that. All I would remind you to do is that is the only value where you have an option to put an open or a closed interval there. Everything else is it can only be one or the other depending on what the graph or what the problem says. I'm going to save warm-ups for another time. Guys, have a good day. I'll see you next time.